This tutorial will illustrate two powerful modeling features of CSiBridge available for use in nonlinear stage construction. Guides, which make for realistic positioning of added structural objects, and the pour concrete remove forms operations, which allow for a correct load distribution between girders and concrete decks. Typically, a realistic construction sequence would be as follows. First, the girders are placed and then subjected to their own self-weight. Next, various sections of deck are poured with the weight of the wet concrete supported by the girders, followed by the concrete curing such that loads subsequently applied are carried by the composite action between the slab and the girders. We will do 4 different load cases, with all 4 load cases being subjected to a dead load of self-weight only. The 4 load cases will be as follows. 1. A linear static case in which the girders and slab work together in composite action to carry the self-weight, the so-called classic approach. 2. A nonlinear stage construction case that will add girders and then the slab. 3. A nonlinear stage construction case that will add girders and then the slab, but will use a guide operation to place the slab for realistic looking deformations. And 4. A nonlinear stage construction case that will add girders and then the slab, but will use the pour concrete and remove forms operations, which will result in the slab weight being carried solely by the girders, meaning that composite action will not happen until after the concrete has cured. This load case will also use the guide operation for placement of the slab. Our model will be for an 80-foot single-span steel girder bridge. The pour concrete remove forms operations are applicable only for steel girder, steel girder, or precast concrete girder bridges. This bridge has 4 girders, and the girders are braced with V-brace diaphragms. Stage construction load cases rely on groups for adding and removing objects. And if we go to the Bridge tab, Groups, we see that the 4 following groups have been added. Bridge sand slab, which is everything but the top slab. Note that items are all checked except for the top slab option. Slab only 80. This is the entire slab from start to end, 0 to 80 feet. Slab only ends. This is 2 30-foot sections of the top slab at each end. This will represent the first concrete pour. And slab only middle. This is a 20-foot long middle section of the top slab. This is the second concrete pour. Our first load case will be the case dead. And if we go to the Analysis tab, we can verify that this is our linear static case. And in this case, the entire model works in composite action to carry the self-weight or dead load. Running the analysis, we find the displacement at the middle of the outside girder is 0.0619. And the F11 force is approximately 95. We will compare these results to values obtained from other load cases. Remember, this load case behaves as if the girders and slab are constructed together and then work compositely to carry the entire dead load. Again, this is not typically how our bridge would be built. Now, let's define our first stage construction case in an effort to incorporate a more realistic construction sequence. On the Analysis tab, we will select a type of nonlinear stage construction. And with our second load case showing, which is called No Guides, No Pours, we click the Modify button. Here we confirm that the nonlinear stage construction option is selected. In this case, we are adding the girders with self-weight and then the slab with self-weight. In this case, the girders will carry their own self-weight, but the slab self-weight will be carried by the entire bridge in composite action. The first stage, called girders, adds everything but the slab and then loads these objects. Again, dead load is just self-weight. The next stage adds in the slab at the ends and loads them again with self-weight. The last stage adds in the slab in the middle and loads it. 3 stages: add and load girders, add slabs at ends, and then the slab in the middle. For this case, save the results at the start and end of each stage. We will now run the analysis for this second load case. With the analysis complete, we will display the deformed shape for the load case 2 at step 0. Here, the girders are first installed, and with the next step, the girders are loaded with their self-weight. Next comes the slab at the ends. The slab is not yet loaded. Note the gap between the girders and the slab. This is due to the fact that even though the slab is attached to the girders, the slab does not know the position of the deformed girders when the slab is added. It only knows where it was defined initially, the original undeformed location. We see that the displacement at the slab prior to loading is 0. The girder displacement below the end of the slab is 0.063. In the next stage, when the slab weight is added, the slab simply settles with the girder. Now we see a slab displacement of approximately 0.033. And if the slab and girder are moving together, we would expect a girder displacement of about 0.096. And indeed, this is what we get. Thus, the relative displacement of the slab is correct, and thus the forces will be correct. The issue is that visually it does not remain connected to the girders. When we go to the last stage and add in the slab in the middle, again we see that the slab and girders are not contiguous. At our point of reference, the displacement at the middle of the outside girder is 0.1172, and the resultant force, F11, is approximately 123. The greater displacements and forces are expected due to the fact less composite action is being utilized. Now we will move on to the next stage construction case. On the Analysis tab, we select Load Case 3, which is called Guides No Pours. and click the Modify button. This load case will use a guide operation to provide a more realistic looking slab placement and hence displacement. Note that the first stage is labeled guides, and in the data area the operation is add guide structure. The group selected is the entire top slab, all 80 feet. Using a guide structure will ensure that as the slab is added to the model, it is connected to the joints of the girders in the girder's deformed position. This will not affect the forces in the girders or the slab, nor will it affect the relative displacement of the slab. That is, the slab will settle the same amount. However, the global position of the slab will be different due to the fact that the slab is deforming from the displaced location of the previous stage and not from the initial undeformed location. The remaining stages, 2 through 4, are the same as our second load case, namely the girders are added and loaded, the slab at the ends are added and loaded, and finally the middle slab is added and loaded. We need only ask for results at the end of each stage. Running the analysis for the third load case, guides no pores, and then displaying the deformed shape for the first step. We see that the guide object is displayed. The guide object has the same geometry and connectivity as the real slab, but with significantly reduced stiffness, no mass, no weight, no loading, and no time-dependent behavior. The guide object will deflect with the girders, and when the actual slab is added, it will replace the object at the same displaced location. In the next step, the girders and their self-weight loads are added in. Note how the guide slab object deforms with the girders. In the next step, the end slabs are added in. Note how there is no longer a gap between the slab and the girders. The last step adds in the middle slab and closes the gap. Checking the displacement at the middle of the outside girder, again the displacement is 0.1172, exactly as before. If we check the F11 component, it too is the same, approximately 123. This is because the load distribution between the girders and the slab is the same as the second load case, only the visual location of the slab has changed. Returning to the deformed shape, we can see that the use of the guide structure makes for a much more reasonable looking displaced shape. The slab and girders are now contiguous. However, we can still make the model behavior more realistic. In load case 3, the girders carried their own self-weight without composite action, but when the slab was added, it was assumed that the slab and girders worked together compositely to carry the weight of the slab. In reality, when the slab is added, it would be with wet concrete that does not have any load carrying capacity. The concrete would not act in composite action until it has had time to cure, and thus the weight of the concrete should be carried by the girders alone. The slab acting as a flange in composite action with the girders would occur only after the forms are removed. We will now take a look at our last stage construction case, load case 4, that will apply the weight of the concrete directly to the girders. However, before doing this, We will switch to the Bridge tab and click the Loads button and then the Slab Wet Concrete Load option. Note that we have defined two concrete pours. The first is for the end slabs and uses the group previously defined. On this form, we could add additional permanent or temporary loading if desired, perhaps for something like formwork. Temporary is added with the wet concrete load, and permanent is added once the concrete cures. In this case, we will leave these as 0. The second concrete pour is for the middle slab. Both of these will have a self-weight factor of 1. Returning to the Analysis tab, we will select Load Case 4, named Guides and Pours, and then click the Modify button. Again, note that it is a nonlinear stage construction case. We now have 6 stages. As in the last load case, the first case adds in the guide structure of the top slab. And the second stage adds and loads the steel girders with the girders self-weight. Changes start with the third stage. Starting here, we will use the pour concrete and remove forms operations. The third stage is called pour ends. Instead of the add structure operation, we will use the pour concrete operation. This will apply the weight of the wet concrete to the girders without using the slab in composite action. Note that the object type is set to concrete pour, and we are applying the load for the slab at the ends of the bridge. We use a new object that we defined in the wet concrete loads definition, CP slab only ends, with CP standing for concrete pour. Now that the loads from the wet concrete is applied to the girders, the next stage will be to add in the stiffness of the slab once the concrete has cured. This is done using the remove forms operation. This works in conjunction with the pour concrete operation to signal that the slab is now a structural object and not just a load. Again, the object name selected is for the slab at the bridge ends. The last 2 stages repeat for the middle slab section what was just done for the slab at the ends of the bridge. Again, using the pour concrete operation, but this time for the CP at the slab middle. This applies the wet concrete loads to the girder, and then we use the remove forms operation to signal that the slab has obtained strength and can work in composite with the girders. Before we run the analysis, we will take a look at the different stages by using the show tree. We will expand the load case just defined with the guides and pour remove operations, and make sure that the show active structures option is checked. Stage 1 is just the guide slab, which will allow the slab objects when added to follow the deformed shape of the girders that they are connected to. Stage 2 adds in the girders. Stage 3 adds in the slab loads at the ends of the bridge, and Stage 4 adds the structural properties of the slab at the ends. Stage 5 adds in the slab loads for the middle section, and Stage 6 adds in the structural properties. It should be noted that when the pour concrete operation is adding the wet concrete weight of the pour region to the girders, it is done using equivalent vertical point loads and bracket loads based on the slab tributary width for each girder. These loads are then reversed during the remove form operation when the actual slab properties and weight are added in. We can now run the analysis for this last load case. Displaying the deformed shape for this load case, with both guides and the pour remove operations, we can step through the stages and see how the model is constructed. At the last stage, stage 6, we see that the displacement is now 0.1373, more than double the 0.619 of the dead case. This makes sense since the girders are carrying the bulk of the bridge self-weight with almost no composite action. If we display the F11 shell forces, the force in the outside girder is now approximately 129, also larger as expected. However, the F11 force near the middle of the deck is now almost zero. Again, this is as expected due to the fact that the slab will not be in significant composite action until after the self-weight loads have been applied. Thus, the pour concrete and remove forms operations will tend to increase the displacement and forces in the girders, while reducing the stresses in the deck, which is a more accurate modeling of actual behavior. In conclusion, when doing a nonlinear stage construction analysis in CSiBridge, the guide operation will provide a more realistic view of the displaced shape, and the pour concrete and remove forms operations will provide for more realistic distribution of girder and slab forces. This concludes this tutorial on using guide, pour concrete, and remove forms operations in CSiBridge.